the design by changing the gap between glass layers, etc. Because sometimes the glass has multiple layers, window glass with gaps in between. So we looked at layers like this, multi-layer. There's a name for that glass, I forget. We already looked into this. And this is another frequency electric surface that is reconfigurable. So it's active FSS. This was also published in Night Transactions. How to make them pre-configurable? We have a whole bunch of pin diodes that can be biased or can be turned off and on. So when you have a surface like this on your wall or normally on a soft wall, you can make your Wi-Fi to go outside your room when you want, and communicate with the outside people outside the room. If you want to block, you can turn the surface on, then it becomes more like a reflector rather than transmitter. So FS is based on square loop apertures. These are the apertures, the loop slots. And then there are 4 pin diodes in every unit cell to control transmission. And that gives 10 dB attenuation when the pin diodes are turned on. So we look at the frequency response over frequency and also response against the angle of incidence for oblique incidence. And yeah, you can find a lot of information in the papers. So given the time, it's about 6:30 now. I think we covered most of the surfaces. I want to get to this leaky wave antenna. Let me check. Also, we did an EBG. So let me share this again. That is stuck. Okay, let's have a problem with moving some of the windows. So PRS we will do with resonant cavity antennas. We covered all this, right? FSS, AMC, ultraviolet surface, absorb, transmit, wideband absorbers, energy saving glass, very quickly active FSS, and shielding. So we get to do shielding and then EBG, then we go to leaky wave antennas. The metasurfaces we will cover with phase correction, phase gradient, beam steering layer. So shielding and EBG. Okay, let me find the slide on shielding. Okay, I lost it somewhere. I think you can. I will find it later. Um, let's move on to electromagnetic band gap. Because I got several slides on that 2004. So, how many of you are familiar with electromagnetic band gap? It was a hot topic for quite a while. People still work on it. We have designed a lot of antennas. It's still active area of research. It's called photonic band gap by optics when it is applied to optics. So these materials are called photonic crystals. At radio frequencies, we call them electromagnetic band gap structures. We call the effect electromagnetic band gap instead of photonic band gap.
Sir, you are not audible. Hello, sir. Your voice is not coming.
Yeah, the computer lost the mic. Now it is back, I think.
Yeah, yeah.
Um, so this is a unit cell of a 3D wood pile. This this type of electromagnetic band gap or photonic crystal EBG structure is called wood pile. You can guess why it is like it's like a pile of woods. This is the unit cell. So we repeat this in all three directions to make a photonic crystal. Now, why these are interesting? These are not metal. These are all dielectric. However, they behave like metal because they stop transmission of electromagnetic waves in all directions. All directions. In 3D photonic crystals or EBG structures have what is called complete band gap. That means it prohibits transmission of electromagnetic waves in all dimensions, all directions in 3D and all polarizations. So to prove this, we build a photonic crystal of this type using alumina rods. The alumina is a dielectric, uh, normally called lumina, but it's a dielectric with dielectric constant plus tangent. And these are the design parameters that has complete band gap over not infinite bandwidth, but good range of frequencies. And when you look at the theory of photonic crystals, these can be done analytically or using software. My postdoc did this using software called BandSolve in different directions about the propagation. And when we design it this way, it turned out that there's a complete band gap from 11.7 gigahertz to 13.5 gigahertz. So this is the unit cell size that is called lattice constant in optical. The optical experts call it lattice constant. We call it period. So it has complete band gap in this frequency range. So gap to mid gap ratio is 12.4% percentage band gap. That means waves in this range, all electromagnetic waves in this frequency band cannot propagate through the crystal in any direction with any polarization, provided that the crystal is large enough. Because the crystal doesn't really reflect or it doesn't absorb, it's all lossless, so it reflects. So you need enough depth of the crystal to attenuate all these waves. Let me check, skip this and go to the end. Yeah, so this is how we measured band gap of this crystal. We build it and then apply two microwave horn antennas with the network analyzer. We measure the transmission, have different polarizations, and this is what we got. One is the predicted curve, the red curve used in finite difference time domain method, and the blue curve is the measured transmission. And this is the band gap. You can see very large drop of transmission in this band. So that is the photonic band gap or electromagnetic band gap, measured band gap from 10.8 gigahertz to 14.2 gigahertz. I think this is probably the first experimental demonstration of uh, band gap of this wood pile in a microwave crystal. After we did this, a lot of other organizations like European Space Agency build photonic crystals uh, at other frequencies, millimeter wave frequencies, and uh, did more work. So, okay, now that is it. Okay, that is the crystal, right? That's not very exciting. You build a big chunk of metal with lot of trouble to make it behave like metal, and metal is a lot cheaper and easier to get a big block of aluminium or copper than building this. So what is the point? And the point is it has a lot of interesting features. One of them is this. Can you see there's one rod missing here, right? This is a periodic structure. This rod, I'm going to take this rod out. Now what happens? One rod is missing. Now that is called a defect in this jargon. And this defect can behave like a waveguide. So we can send a wave through this defect, and that's called a defect waveguide. So you can calculate the frequency versus wave vector or wavelength of this defect waveguide and show that it can propagate waves over a certain range of frequencies from, in this case, 11.8 to some 13.4 gigahertz or so. And now you can see the defect waveguide. It is this one. Along this line. So when we come back, 6:40. Let's say how much you can do. For about 5 minutes. I think I can show a little bit. Go a little bit further. So this defect behaves like a waveguide, okay? But we have to apply a wave to this defect. For that, we have to design a transition. This is a normal waveguide, metal waveguide, connected to a coaxial. This is another normal metal waveguide connected to a coaxial. So we can connect coaxial to our network analyzer to apply a wave through this. And that's what we did. These are the design details, looking from the top. This one is looking from the side. And we can actually get very good transmission through this defect. So the blue curve here is a transmission predicted, and the red curve is the measured transmission. It just behaves like a good waveguide, transmitting wave from one end to the other. So only 0.4 dB transmission loss. That is because of the coaxial to rectangular couplers we have at the two ends. Now this is the interesting part. How does it work? So this is the wave we applied. Don't know why it stopped. Let me try. So this is the wave, this is the electric field. You can see that it's a propagating wave. It doesn't reflect much. Um, and the transition here at the junction, it doesn't reflect, right? It's that is the way you design. It wasn't too difficult to match the waveguide to the defect waveguide. The peaks are different, and that is because the wavelength in the defect waveguide is different to the wavelength in the rectangular metal waveguide. So this is the metal waveguide. It's very annoying. I think I have the same in another slide packers. Which one? Okay, I'll try to find the one after we return. So when it is frozen, you can see it better. So this is the wavelength from here to here. Red are the maximas, blues minima. That's one wavelength. That's the defect waveguide wavelength. And the rectangular waveguide wavelength is longer. So this is in linear scale, the field. Now it's very interesting when you look at the field in decibels, dB scale, because then you can see this very weak field penetration into the crystal. So you can see that field is not zero, it decays exponentially, becomes almost zero at the end. That's how photonic crystals work. So it has to be thick, this thick, to behave like metal, to guide waves. Otherwise, you can expect the waves to leak through the crystal. As long as you have a crystal of good thickness, then it can behave like a waveguide. It can guide the waves just like a metal waveguide. Not exactly like metal waveguide, but similar to a metal waveguide. Okay, so we take a break. We return at 2 p.m., right? Your time for the last lecture today.
Yes.
So in that one, I will finish the EBG.
Okay.
And get to the leaky wave antenna part.
Okay. So audience, this session is open for audience. If you have any doubt, you can ask.
Yeah, I think we will. I will ask questions when I return
Okay. No issues.
because I need full 45-minute break.
Yeah. Okay, sir. Thank
I'm
you.
already losing my voices.
Okay, sir. No issue.
Okay, keep all the
Mm.
questions and I will answer when I come back.
Okay, sir. Thank you. Okay, thank you, audience. We'll resume this next session at 2 p.m.